So our first talk is from Ivo Pink, who's a PhD student just finishing up within the Institute, and he's going to be talking about predicting future floods from climate ensembles.
Yeah, hello everybody. My name is Ivo Pink, and I work on predicting or simulating the evolution of flood risk. So I work on, or I use simulation, environmental models to investigate how the spatial and temporal variability of flood hazards change. And I do this in the Karnali Basin. So we are going back to the Karnali River. And the Karnali River is a very steep Himalayan catchment. And once it exits the mountain front, it transitions from a very steep, very steep river to a shallow river. So it enters an alluvial plain, and this plain is constantly reworked and reshifted. So if we want to understand how floods change in space and time, we first of all need to understand how does the amount of runoff change in time, so how does climate change impact the flood flows. But then we also need to consider how the elevation change, because the elevation is, ultimately determines where the water will flow. So I want to start off with our simulations to assess the impact of climate change on flood flows, and for this we established a hydrological model for the catchment, and we run it with historic data of and then we project it further onto the future. So this is the medium emission scenario, so the current path that we are on right now. Unfortunately, the yellow is not very visible here, but we also run it for a high emission scenario, which is better visible. Anyways, we have uncertainty relating to the hydrological system, so we have incomplete knowledge of the Karnali River, of the hydrology of the Karnali River. So we have uncertainty in that, and then we of course have also uncertainty in the climate projections. We don't know the future climate. So we use an ensemble modeling approach to account for these uncertainties. So first of all, we set up our hydrological model and maintain 64 different realizations of this model to capture the hydrological uncertainty. And then we use this ensemble with with the data from 12 climate models. So we capture also the uncertainty in the climate predictions. And this gives us an ensemble of round about 750 models. And we can use this to quantify the change in flood flows. And we do this by conducting a flood frequency analysis. So a flood frequency analysis assigns a frequency to a flow. In this way, it's basically a way of standardizing flood events. We can then compare the magnitudes of flows with similar frequencies. And we do this for the 100-year event. So an event with a flow that occurs once every 100 years, or that has an annual occurrence probability of 1%. So for each scenario, because we have an ensemble, we predict an ensemble of flood magnitudes. And on the y-axis, we plot the amount of simulations that are at that threshold or below. So for example, at the 50th percentile, we get a magnitude of around 11,000 QMAX for the baseline scenario. This means that 50% of our predictions for the baseline scenario have a magnitude less than 11,000 QMAX and 50% higher. So if we move further up the scale, it gets less likely because less and less models predict a higher flow. And if we move down, it gets less likely because less and less models predict a lower flow. So for our most probable range, in the near future, the flows increase by 20 to 30%. And if we look into the farer future, this increases to 30% for the medium emission scenario and 80% for the high emission scenario. So a massive increase in flood flows. And now we want to simulate how the elevation change. So we use the predicted flows and feed it into a morphodynamic model to see or to simulate the changes in elevation over time. And these predicted topographies we can then feed into a hydrodynamic model to simulate the patterns of the floodings. And this is for the current topography. And you can notice something very interesting, and that is that the water flows actually away from the river. So the Karnali River flows on an alluvial plain or on a fan. So basically, it carries the sediments from the mountains and it deposits it in the riverbed. So the riverbed elevates, and at some point it's actually higher than the surrounding area. So it's very important to consider the morphological evolution, because at some point the river will break and it will swipe. So over centuries and millennia, the river actually swipes across the whole fan and fills it up gradually. So what does an increased flow of 40% or even 80% means for this evolution of the fan? And thanks. Yeah.